right, have your homework handouts out if you would please. And hold them up so that I can see that everything is completed. Excellent. You had 3 problems and then the one from the book. Number 1, you're converting to trigonometric form, and we had a -5, positive 2i. What do I need to do to convert into the trig form? Because we spend most of our time, frankly, converting out of the trig form. How do we convert into trig form, Quentin?
To get the r, you take the square root of 25 plus 4.
There we go. The square root of a squared plus b squared. And so we'll square the -5 to get 25. We'll square the positive 2 to get 4. Again, you're not squaring the I because b is the coefficient of the I. And we end up with kind of a big, ugly whatever. Okay, square root of 29. There's our r. And then what about the other part of the trig form, Jamie?
Take the tangent of the array.
Good. A moment ago I said you'll square the -5, but again, because you're squaring, don't even really worry about positive and negative. It's just 5 and 2. Here again, do the same thing. It's really just 5 and 2, and if you take the 2 over the 5 and take the arctangent of that, what does that initially give you for your theta?
21.80 ...
But we now need to account for the quadrant, remember. And what quadrant is -5, positive 2i in? Quadrant 2. So once I've got the 21.80 blah 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 degrees, I need to then subtract that from 180 to get what actual theta?
158.2.
And we'll round off just that 10th place, remember, just a single decimal. And so what is my trig form number going to look like? Back to Quentin.
Square root 29 times cosine 158.2 plus I sine 158.2.
And of course, we wouldn't want to forget the degrees on that either. But again, if you wanted to check your answer, you would distribute it, and you should get approximately -5 when you multiply here, and approximately a positive 2i when you multiply there. Okay? If you wanted to check your answer that way. Questions on this? All right. The second number, you were converting or multiplying numbers that were already in the trig form, and to multiply, what do we do first, Jamie?
We multiply the r values.
And when you multiply the 5 times the 4?
20.
20. And then the next thing, Quentin?
I have
So you end up with the cosine of
210
plus I times the sine of the 210 degrees. That's multiplication. The multiplication's done. Now we need to convert back to standard form, Jamie.
We get a reference angle which is 90 degrees.
Ooh, for 210? Reference angle 90?
30 degrees.
30 degrees, there we go.
And we'll know that same quadrant 3. And then take the cosine of 30 and get square root of 3 over 2. And then we get the sine, and it's 1 over 2.
By the way, y'all kind of noticed that if one is square root of 3 over 2, the other's a half. If one's square root of 2 over 2, the other's square root of 2 over 2. If one's 0, the other's 1. If one's 1, the other's 0. So we're kind of noticing the patterns here. But we do want to look out for that quadrant, Jamie. You said quadrant 3.
Yes, and so it's going to be negative for both.
Right, and then
We distribute the 20.
to get?
Negative 10 to the square root of 3 minus 10 I over 2.
Remember, the 20 and the 2 cancel when you multiply here as well, because you're distributing the 20, multiplied by both of them. How do we do on number 2? Hey, that right. All right. Number 3, we're going to divide. So class, we start by doing what to the r values? Actually dividing to get?
2.
And then what do we do to the theta values?
subtraction
To get the cosine of
270
plus I times the sine of 270 degrees. And Quentin, go ahead and convert it back to standard form for us.
square root angle is 90 quadrant 3 or 4. The cosine of 90 is 0. Sine 90 is 1. And your quadrant negative 1i.
Good, and we don't need to worry about the 0. You're like, well, quadrant 3 is positive, or negative is quadrant 4, it's positive. It doesn't matter, it's 0 anyway. And so when we quote distribute the 2, unquote, we get
Negative 2i.
negative 2i. And there we go. Did you get that for the last one? Questions at all on the first part of the handout? Not so much the problem that I gave you from the book, but the part that was printed on the handout. Any questions on those? Well, let's take the quiz over those, and then we'll go back over what we looked at yesterday specifically. Clear your desks for now, if you would, please, except for a clean sheet of paper and a pencil and a calculator. Clean sheet of paper, pencil, calculator, everything else away. First and last name at the top of your paper, along with today's date, which is 1/28/22. 1/28/22, today's date. And this is quiz 28. Quiz 28 on the 28th. Being nosy here, I just noticed you have stickers not only on the face but on the hand. And then what's on the wrist?
They're like the temporary tattoo bracelets.
Interesting. There's gold glitter all over. All right, very nice, very nice. All right. I didn't notice it in homeroom. So all right. Let's take a look at the quiz very quickly before we get started. Numbers 1 and 2, very straightforward. You're just converting to the trig form. Again, round angles to the nearest tenth. Numbers 3 and 4, you're converting to the standard form. Number 5 through 8, you're either multiplying or dividing and leaving your answers in the standard form. Any questions?
So we just multiply and divide, nothing else on 5 through 8?
Well, you're going to multiply and divide, and then you're going to leave your answers in the standard form,
Okay.
just like we've been doing. So number 3, all you're doing is the converting to standard. There's no preliminary steps. 5 through 8, just add those preliminary steps of multiplying and dividing first, then you convert over. So technically, there's 6 problems you're converting to standard. go. All right, let's go ahead and take a look at the other part of your homework now. And page 187, number 14. So I believe that was on your handout as well, or you should put it on the handout. Yesterday, we talked about how to raise a trig form complex number to some power. We just said raise it to, say, the nth power. This is actually, this concept actually is called DeMoivre's theorem. If you go and add that to your note, named after the mathematician Abraham DeMoivre. I can't write a cursive R to save my life. DeMoivre's theorem. It's spelled DeMoivres, but D-E-M-O-I-V-R-E-S. It's in your textbook too, if you look back like a page or so. DeMoivre's theorem. And he's the first one who kind of came up with this concept. It's not a difficult concept. We're going to expand on DeMoivre's theorem and the reason why this actually gets named after him, because of the power that this has when we apply it to roots. And I kind of alluded to that yesterday. But for now, let's take a look at DeMoivre's theorem in its more basic application, and that's raising to a power. For instance, supposing I had, say, a 2 times the cosine of 40 degrees plus I times the sine of 40 degrees, and I wanted to cube this number. What would we do to raise a complex number in the trig form to a power? Quentin?
Cube the 2.
Okay, we start by raising the r to whatever the n power is. In this case, we would just simply cube the 2 to get 8. Then what would we need to do?
Multiply the exponent by the angle.
Good, we're going to multiply the angle by that exponent. So not cubing the 40, but multiplying the 40 by 3 to get the cosine now of 120 degrees. Plus I times the sine of 120 degrees. And of course, at the end, we can convert back to the standard. Our reference angle here, class, is 60 degrees, because we're in quadrant 2. And cosine of 60 and the sine of 60. Though we should account for the quadrant here. I failed to do that. Negative on this one, positive on this one. Of course, don't lose the I. Then we'll distribute the 8 to get what final answer here, Jamie?
Negative 4 plus 4i plus the square root of 3.
There we go. Okay, so this is kind of what we looked at yesterday. You had one for homework, and it was number 14 from page 187. Number 14 was 2 times the cosine of 120 plus I times the sine of 120 degrees, and you were raising all of this to the 5th power. And what did we do here, Jamie? Kind of walk us through.
I raised the 2 to the 5th power and got 32.
All right.
Then I multiplied the 125 by 5 and
Okay.
got 600. But then we have to subtract 360 from it.
So we really end up with 32 times the cosine of
240.
240 degrees plus I times the sine of 240 degrees. All right.
Then we convert to the standard. And,
All right. And what's the reference angle, class?
Yes.
60 in quadrant
3.
3. And so the cosine of 60, once again,
And then
a half. In this case, negative, because quadrant 3, the sine is the 60.
So 32.
And once again, it's
Negative.
negative because it's in quadrant 3. We'll keep the I. Distribute the 32, and what's our final answer here, Quentin?
Negative 16 minus 16 minus square root of 3.
And there we go. And did we get that answer for number 14? Let's take a look at number 16 now, because number 16's got a little bit of a weird twist. Here we've got 2 times the cosine of 300 plus I times the sine of 300. And it's all being raised to the negative second power. Well, we know this. Negative exponent means reciprocal. But which part of the complex number in the trig form actually gets raised to the negative power? It's really only this 2. So it's really only the 2 to the negative second, where I have to think reciprocal of 2 squared to get class 1/4. With the theta value, with the angle, I actually have to multiply by the negative 2. And so that's going to give me the cosine of negative 600 degrees plus I times the sine of negative 600 degrees. There we go. Make sense? The same process we would have used before, except because we have a negative angle.
We have to add.
Add the 360, or since it's so big, maybe add 2 360s or 720 to get a 4th times the cosine of 120 when we add the 720 plus I times the sine of 120. Almost wrote a 720 there. And we'll go from here. Again, reference angle. All 3 in a row. All right. And the quadrant, 2. And so the cosine of 60. A half. Of course, we'll say negative in quadrant 2 and the sine of 60. And we'll say positive, keep the I. And we've got to distribute the 1/4 to get what here, Jamie?
Negative 1/8 plus I times the square root of 3 all over 8.
And there we go there. All right, questions on negative exponents? All right, I want you to do numbers 15, 17, and 18. They're on page 187. Again, if you haven't already, you can flip back and look at page 184 very briefly. And we've got a very lovely picture of Abraham DeMoivre. But anyway, there you go. let's go ahead and take a look at these, see how we did. Number 15, what did you get initially when you raised to the power and multiplied the theta times the exponent, Jamie?
A 1 times 6 cosine of 1080 degrees and plus
I sine of 1080. And of course you subtracted 360 a few times, right? To end up with 81 times the cosine of 0 degrees plus I times the sine of 0 degrees. Did you happen to remember what we said about cosine 0 plus I sine 0? It's a big fancy way of saying 1. It basically becomes 1 plus 0i. So our answer is simply 81. So when you raise that to the 4th power, you get 81. Interesting. Number 17. What did you get when you raised to the 6th power initially, Quentin?
4096 cosine 1020 plus I sine 1020.
Good, and then you subtracted 360 a couple of times, ended up with an angle of just
300.
300. Okay, I'm misreading my writing here. It's kind of sloppy. 300. I saw a 30, and I guess the other 0 got erased. It's like I got 30. No, that is 300. All right. And so ended up reference angle 60. You get the quadrant 4. You get the positive half. You get the negative square root of 3 over 2. You distribute the 4096. You got
2048 minus 2048 I square root of 3.
Yeah, big old number there. 2048 minus 2048 I square root of 3. Questions on that one? And number 18, a little bit easier here. You initially had what, Jamie?
1000 times cosine of 675 degrees plus I sine 675 degrees.
Good. We had to subtract 360. Looks like I've got it subtracted twice, but that can't be right. I must have only subtracted it once. We get, yeah, there it is. Okay, I see it now.
I got 315.
315 is correct, yes. And so reference angle 45, quadrant 4, the square root of 2 over 2's, but negative for the sine, positive for the cosine. You distributed the 1000, you got
500 times the square root of 2 minus 500 I square root of 2.
Good. 500 square root of 2 minus 500 I square root of 2. Are we perfect on all 3 of those? Are there any questions at all on raising to powers? But again, could we raise to power in the standard form? We could, right? It'd be obnoxious, Pascal's triangle, right? But we could do it. There's really only one thing you absolutely have to have the trig form for. And it's the whole reason we talked through this whole thing. There's all kinds of things you can do in the trig form, but there's one thing that you have to have the trig form for. And it's something that if we go back to Algebra 2, and I've referenced this, alluded to this a few times, we said we've got, for instance, the cube root of 8. And I said there are how many cube roots of every number? 3. But you only know 1. One of them is 2. And then there's another one, and another one. Just like there are 2 square roots of every number. What are the square roots of 25, class? Positive 5 and negative 5, right? Or positive, negative 5 is generally how we say it. How many 4th roots are there of every number? 4, right? There'd be, for instance, 3 and negative 3, 3i and negative 3. I remember we had this a couple times. We did equations where we took the 4th roots, right? So there's multiple roots here, but with that cube root, we were kind of stuck. Like, what do we do, right? And I said, I can't teach you what they are yet. Or we work a problem where we said, well, there's going to be 6 roots. For instance, like the 6th root of 64. We used to say it was 2. But you could probably guess another one of the roots. Negative 2. But there's 4 more roots. And I said in Algebra 2, you can't find them yet. You need trigonometry to do it. And so for 2 years, you have been waiting for the truth, waiting for this knowledge. This is a huge day in your lives. Today is the day I teach you how to finally solve that missing thing, that thing that's been evading you for years, that thing that's kept you up sleepless nights, wondering, but what are the other 2 cube roots of 8? Today, we will answer that question. For the record on YouTube, they do not look nearly as excited as I'm making it sound, but whatever. All right. I want to take you back to another algebra concept for a moment, and that was that if I wanted to write the square root of 25, I could write it as 25 to the 1/2 power. You remember that? So similarly, the cube root of 8 could be written 8 to the 1/3 power, or the 4th root of 81, 81 to the 1/4 power, or the 6th root of 64, 64 to the 1/6 power, right? So we're good on this. Okay, that's integral because that means we can turn any root into a power. And therefore, DeMoivre's theorem can be used in this form. The key is to start by writing the radicand as 25 times 1, for instance, here. But we're not just going to write a 1. We're going to write a very fancy-looking 1. We're going to write this as 25 times the cosine of 0 degrees plus I times the sine of 0 degrees, all to the 1/2 power. We're going to put the number, the radicand, into the trig form and use a fractional exponent to take the root. What you're going to end up doing here is you're going to end up raising, first of all, this to this power, meaning you end up taking a principal root. That's the root that the calculator would give you. The principal square root, or principal 1/2 power of 25, is, of course, 5. And then you would multiply the theta times the exponent to get, well, what's 0 times 1/2? 0, plus I times the sine of 0. And, of course, this is still just a fancy way of saying 1, so we still just get 5. Well, that's good because that's one of the roots we knew we would get. But we also have a way of getting the negative 5. There are 2 square roots. Well, everything we're doing here is based on function, meaning only one value you can get out. The principal root is only one value. When you take the cosine or the sine, that is only one value because they are functions. So what we're going to do is we're going to creatively write this again. But I'm not going to say 0. I'm going to go coterminal with 0, and I'm going to say 25 now times the cosine of 360 degrees plus I times the sine of 360 degrees. Do you see that this is the same thing as this? But by using the coterminal angle, when I raise to the 1/2 power, I'm still going to take the principal square root, or 1/2 power of 25. Still just 5. But now, when I multiply theta by the 1/2, by the exponent, I get the cosine of 180. Plus I times the sine of 180. Well, what's the reference angle of 180? 0, but it's in quadrant 2, or you could say quadrant 3, either way. Well, the cosine of 0 is still 1, but in quadrant 2 or quadrant 3, the cosine is negative. The sine of 0 is still 0, and we don't have to worry about positive or negative. And when I distribute 5 times negative 1 plus 0i, I get negative 5. Now again, do we need DeMoivre's theorem to take square roots and get your positive negative? Of course not. But this is the process we're going to use for things like this. So on your paper, let's go ahead and take the cube roots, all 3 of them for the first time ever, of 8. The 3 cube roots of 8. Now, as a reminder, if the problem simply said cube root of 8, or square root of 3 cube root of 8, same thing, right? If the problem said the cube root of 8, it means the principal cube root of 8, which is just 2. But if you had, for instance, x cubed minus 8 is equal to 0, and you sent the 8 over to the other side as a positive, and you took the cube root, you are expected to provide 3 answers because it's a cubic equation. This is the time where you would need to be able to use this. Make sense? All right, so let's take the 3 cube roots of 8. For starters, I said we're going to rewrite the radicand as the radicand times 1. But I'm not going to write 1. I'm going to write cosine 0 plus I times the sine of 0 degrees. And we're going to raise it all to the 1/3 power. But again, that is functional. It's all based on what the calculator would put out, which means it's only going to give you one of the roots. So we're actually going to do this, since we need 3 cube roots, we're going to do this 3 times. I'm going to write it again. 8 times the cosine of 0 degrees, but I'm going to write that which is equal to 0 degrees. 360 plus I times the sine of 360 degrees. And raise that to the 1/3 power. I need another one. What do you suppose I'll put here? 8 times the cosine of, what did you say?
270.
Coterminal again. Not 270, you're lisdexing. 720.
Oh.
I think that's what you meant. All raised to the 1/3 power. Make sense? They are all cosine 0 plus I sine 0. Right, the cosine of 360 plus I sine 360 is 1. The cosine 720 plus I sine 720 is 1. Anything coterminal with 0, cosine that plus I sine that, if it's coterminal with 0, they're all equal to 1. So this is still just 8 to the 1/3, 8 to the 1/3, 8 to the 1/3, but it's going to produce different results every time. For starters, we always just take the principal root of the 8. The principal cube root of 8 is, that's going to be true for all of these. Times, and then what we're going to have to do is multiply theta times the 1/3. Well, 0 times the third class gives me 0. So we get cosine 0 plus I sine 0. And of course, since that whole thing just equals 1, 2 times 1 is... And the first root you find will always be the principal root. No issue there. The next time I do it, though, it's going to be the cosine of 360 times 1/3. 120 plus I times the sine of 120 degrees. The next time you do it, it's going to be 2 times the cosine of 240 plus I times the sine of 240 degrees. Well, in both cases, what's the reference angle? But here it's quadrant, and here it's quadrant. In both cases, what's the cosine of 60?
1/2.
1/2. But quadrant 2 cosines, quadrant 3 cosines, still negative. All right, sine of 60 in both cases. Square root of 3 over 2, and of course don't lose the I. But in quadrant 2, sine is, but in quadrant 3, sine is. And in both cases, we have to distribute the 2. When I do, I get a -1 plus I squared of 3. Here, I get -1 minus I times the square root of 3. And I told you in Algebra 2, there are 2 more roots. They're both complex, and you need trigonometry to find them, and there they are. It's like a burden's been lifted off your shoulders. Like, yes, now I can truly solve any equation. Because that was the only thing you couldn't do in Algebra 2. After all these other equations, but that one thing I said you just can't. You're not able to. Now you're able to. Do you feel fulfilled? Quentin seems less than enthusiastic. All right. Let's practice this. Although we already know what our answers are going to be, let's practice it with the 4th root of 81 to get a feel for the process here. By the way, before we do, I want to point something out. Because I know what you're thinking. You're thinking, you say there are 3 cube roots. Couldn't I do this infinitely? Couldn't I do 8 cosine of 1080 plus I sine of 1080 and take the 3rd root of that? Wouldn't that give me more than 3? And I could do 1440 plus I sine 1440. And you get the idea, right? Yeah, see? Well, do you notice the pattern though? When you take a third of 360, it gives you 120. You take a third of 720, it gives you 240. What if I did try to get one more? Ha ha ha, I have this now. All right, and I raise all this to the 1/3. I'm like, I'm going to get a 4th one. I'm going to prove him wrong. And you multiply 1080 times a third. What does that give you? $360, which is coterminal with 0. And it'll go right back where you were before. And so if you kept going, you keep getting these same 3 answers over and over and over again. So DeMoivre's theorem is foolproof. You really will only get the 3. So if you got carried away sometime. Now I also want you to notice, you said 360. Notice the pattern. 0, 120, 240, if you did keep going in B360, what's the numeric pattern here? You keep adding 120, right? All right, keep that thought in mind. Let's take a look at the fourth roots of 81. Again, we already know what the answers are going to be. We're doing this for the sake of the practice of figuring out the process. Let's start by rewriting 81 as 81 times 1, or 81 times and we're going to raise all of it to the 1/4, because we're taking the fourth root. Now, I'm going to let my laziness take over a little bit here. You ready? I know all of these are going to be 1/4 power, and I know there's going to have to be how many of them? 4 of them. Every time, it's going to be an 81, right? And my angle here is going to have to be coterminal to 0. But I'm too lazy to write the rest of that. And the next time the angle is going to be coterminal again. And the next time it's going to be coterminal again. 1080. Right? I don't need to write all the extra little stuff in there, because I'm too lazy for that. Make sense? Then, I'm going to start by taking the principal fourth root of 81. It's what the calculator would give you, and of course that is... 3, because 3 to the 4th is 81, so 3 is your principal root. And again, you could do 4th root of 81 on the calculator, or 81 to the 1/4 power, it would give you the 3. And of course, we know that the first one's going to be cosine 0 plus I sine of 0 degrees. And of course, that's just going to equal, I don't even have to do any math for that, right? But when I raise the 360, this one to the 1/4 power, I'm going to multiply the 360 times 1/4 to get 90. Plus I sine of 90. Then I'm going to take 1/4 of 720 to get 180. Plus I sine of 180. And then I'm going to take 1/4 of 1,080. 270. Did you find that on the calculator, Jamie, or did you guess?
No, I found it on the calculator.
You did it on the calculator. Could you have guessed?
Yes.
Because math is always going to follow patterns. If the gap between the first two is 90, that's the continued gap. 0, 90, 180, 270. And if you were forgetful, so carried away with joy and enthusiasm, you accidentally did a fifth one, what would be 90 more? 360. Oh, that'd take you back, right? And that's how it's always going to work. In fact, if you were to graph them, right, that last one, remember, was the cube root of 8, right? We said it was -1 plus I squared of 3 and -1 minus I squared of 3, remember? Well, watch where these points would be plotted. 2 on the complex plane, -1, and then up square root of 3i, -1 down square root of 3i. 120 to here, another 120 to here, 240, and another 120 will put you back at 360. These points all have a radius of 2 and are arranged perfectly symmetrical. Here, you're going to have 3 cosine 0 plus I sine 0, 3 cosine 90 plus I sine 90, 3 cosine 180 I sine 180, 3 cosine 270 I sine 270, radius of 3 for all of them, but 90-degree angles, which is why you get 3, 3i, -3, and -3i on the Cartesian plane. It's always a pattern. Knowing that, as lazy as we thought we were being here, we can be even lazier moving forward. Real quick, though, I want to finish it out. We know the cosine of 90 is 0, but the sine is 1. So 1i, when we distribute, there is the 3i. Here, 180 is the opposite of 0, backward. -1 and 0i, -3. And here, cosine 270, that's 0 because reference angle 90. Here, reference angle 90 is 1, but quadrant 3 or 4 negative. We distribute, we get -3i. And there they are. Patterns are what is going to make this not a nightmare. So that on Monday in our next lesson, when we try to find the eighth roots of 1, it doesn't take all day. We fly through it because we see patterns. When we take sixth roots of 64, we're able to fly through it because we see patterns. That's what we're going to work on Monday in our next lesson. We're going to give you no homework tonight. Let's take the weekend off from some work. When we come back Monday, we'll pick back up with DeMoivre's theorem and go from there. Have a wonderful rest of your day, and you are dismissed.